Real exam questions. This is question 71 concerning slab design. Determine the structure of a classroom with an effective dimension of 13.5 by 12 meters by means of a one-way bearing concrete slab. The floor slab rests on 2 centimeters thick masonry. Determine the needed floor depth with a finish of 2.3 kilonewton per square meter and a mobile load of 3 kilonewton per square meter, all in characteristic value. And this floor must meet the ductility requirements. The minimum distance between the bars is 100 millimeter, and the concrete quality is C2530 and the steel quality BS500. The classroom is 13.5 by 12 meters. So to meet the one-way direction slabs, to make it possible, we must be sure that the largest distance of the slab is more than 2 times the shortest distance. So this means that we have to cut the classroom into 2 areas, one with a span of 6 meters and the other also a span of 6 meters. If you do the cut in the other direction, then the span will be bigger, so it's less interesting to do. Plus, it will not be a one-way bearing slab, not totally. So now we look at the shorter span of 6 meters. The effective span is, of course, the minimum of half the thickness of the slab, but we don't know this thickness yet, and half the width of the port point. And the net distance was 6 meters because this is going right in the middle of the beam, and the beam is underneath the slab. So we have 6.1 meters, but this is assuming that H must be bigger than 200 millimeters. So, which is expected in fact, but we have to check this. So when H is bigger than 200 millimeters, then the effective span is 6.1 meters. The first estimate of the required depth, we have to do that because we need to calculate some loads on the slab. So the estimate required depth is the effective length divided by D, the optimum depth or the effective depth D. And this ratio must be between 18 and 26. 26 for slabs who are not who are light loaded, not very hard loaded, and 18 is for bigger loads on the slab. So we'll take somewhere in between. So we make a guess that the effective depth is the effective length divided by 20 and gives us 305 millimeter for D. Now we also have to estimate the diameter because the concrete cover for an indoor slab is 15 millimeters plus the largest diameter you use in the reinforcement, but we don't know the reinforcement yet. So that's the second assumption. We start with diameters 20 millimeters and we have a concrete cover of 35. So our first estimate of the depth of the slab is the D, 305, plus the 35 plus 10 millimeters, gives us 350 millimeters. The total load is then the permanent load, which is the weight of the slab, which is 0.35 times 25, plus the finish of the floor, times 1.35 and 1.5 times the mobile load of 3. So the total load in ULS persistence is 19.42 kilonewton per square meter. From this, we can calculate the maximum bending moment of 90 kilonewton meter per meter. And when we got the bending moment, we can now calculate the needed effective depth for ductility to guarantee that there is enough ductility, which is given by this formula. Taking note that MSD in this formula is in kilonewton meter per meter and FCK is in megapascal. So the needed ductility depth is 146 millimeters. The corresponding reinforcement is then the bending moment divided by the lever arm and divided by the yield strength of the concrete, of the steel, sorry. Because we are working at the ductile, there is a zeta ductile corresponding with this, which is 0.813. And you will need then for as reinforcement in the slab of 1,743 square millimeters per meter. So we can do it with 6 diameters 20. We started with a diameter 20, so we stay with the diameter 20. So it's 1,885 square millimeter per meter. The total depth is then the D, the D ductile, which is 146, plus the concrete cover, 35, plus the largest diameter. The point of gravity of the largest diameter gives you 191 millimeters. But this 191 is different from the value that we started with. So you see that we need less depth of concrete. So this will lower the load on the concrete because this is small compared with the permanent loads. So this can have a rather big influence. So we will take the next best of the depth, needed depth of the slab, which is not 191 because we know the load will diminish, will get smaller. So we take a gamble and we take 180 millimeters. So the effective length is now half of the 180 millimeters. Remember, last time we assumed that the slab was bigger than 200 millimeters. So that's why we recalculate the effective length of the span, and we have 6.09. It's not a big difference, but it's just a difference. The total load is then 0.18 times 25 plus 2.3 times 1.35, which is the permanent load, plus the mobile load gives you 13.68 kilonewton per square meter, which is much smaller than the previous one. The corresponding bending moment is then 63.4 kilonewton meter per meter, and the needed ductile depth of the slab is then 123 millimeters. The corresponding reinforcement is then again the bending moment divided by the lever arm corresponding with the ductile times the yield stress of the reinforcement. And we need 1,457 square millimeter. We can do that in 5 diameters 20, which gives you 1,571 square millimeters per meter. So the total depth is now D, 123, plus the concrete cover, 35, plus the point of gravity of the reinforcement, so one layer diameter 20, so it's 20 divided by 2, and we have now 168 millimeters. But we started with 180, so we are still not there. We round, we make it the depth of the slab where we'll start with, we'll make it equal to 160. So for this slab depth, the effective length is then of effective span is then 6.08. The total load is then 13 kilonewton per square meter. The maximum bending moment is 60 kilonewton meter per meter, and the required ductility depth is then 119 millimeter. We recalculate the reinforcement and we find 1,426 square millimeters. This can be transformed to 5 diameters 20, which gives you 1,571 square millimeters per meter. And the total depth of the slab is the effective depth plus the concrete cover plus the point of gravity. It's 164. So we started with 160 and we end up with 164. So 165 is okay. So that's one solution. 165 is the total depth of the slab plus the reinforcement of diameters 20 with center to center 200 millimeters. Now the center to center is bigger than the total depth. So in most cases, we will avoid that. So another combination is 10 diameters, 14 millimeters, which give you almost the same reinforcement, but the spacing between the reinforcement is better, it's 100 millimeters. And when you redo the calculation, you will see that or you can just see it here on the bottom. And instead of 20, you fill in 14, you will have 161 millimeters. So it means 160 millimeters as total depth will be fine. So in total, for a depth slab of 160 millimeters, the reinforcement is 10 diameters 14. For a slab thickness of 165 millimeters, the reinforcement is 5 diameters 20, and we prefer this as a solution.